Well, good morning, everyone. I've got the top of the hour. Let's go ahead and get started. We want to welcome you to our March 2026 edition of From Research to Implementation, our monthly webinar series that we do. It's important to us here that we find ways to implement the research that we do. And this is one of our ways to share that information out to as many people as possible. So today's topic is cracking tests correlated to field performance. And this is so important as we move towards balanced mix design in our asphalt mixtures across the nation and even beyond there. So with us today, we've got obviously Nathan Moore. We also have our director here at NCAT, Randy West, and we have David Vivanco, who is part of the Oklahoma DOT. So Nathan is the assistant director for the test track research here at NCAT. He oversees all of the test track research programs. Prior to that role, Nathan was in our laboratory, where he was there for about 8 years, doing all sorts of great work, specializing in balanced mix design and friction testing. He's got both his bachelor's and his master's degree from Auburn University, and he's a licensed engineer in Alabama. Most of you are looking at basketball for March Madness right now. He's looking at fixing a section out on the track. So his bracket is having to do with cold feed bins and binder types and so forth. Uh, Randy West is the director here at NCAT and the research professor. He's according to this bio, he's the best boss I've ever had. He's worked as a pavement engineer for 38 years, the last 22 here at NCAT. Prior to that, he worked for APAC for about 7 years, managing their corporate technical services group. But he began his career with Florida DOT as their bituminous research engineer there. David Vivanco, he serves as the asphalt branch manager for the Oklahoma Department of Transportation, where he leads the state's asphalt materials program. He's got a PhD in civil engineering from here at Auburn University with NCAT. He brings extensive experience in BMD, recycled materials, and asphalt pavement testing. David has also been instrumental in advancing Oklahoma's implementation efforts and looking at the different ways that they are using performance tests to engineer their mixes. He's an active contributor in national research efforts and regularly collaborates with industry and academia to bridge between innovation and field application. So that's our lineup today. We've got some really great stuff. We saw some of this at TRB, and Nathan and I were texting each other. We got to have this on our webinar series. So a couple reminders real quick. Please keep yourself muted. Put your any questions that you have in the chat box, and Nathan and I will divvy those up towards the end and make sure that we got them to the right presenter. Given that, Nathan.
Thanks, Travis. One more, I'll add one thing to David's bio. David is the example that we use training new students why not to wear nice shoes in the asphalt lab. You can ask David about that sometime.
Nice.
Um, so, welcome everybody. Really glad to be on this webinar. This is a really exciting topic, one that's actually near and dear to my heart, as we'll see here in just a moment. But for anybody who may be new to our format, I'm going to briefly introduce the topic, quick introduction, quick lessons learned, over the years, and then Randy is going to dive much deeper on the NCAT side of research regarding cracking tests and how they relate to field performance. After that, we'll kick it to our industry or agency friend. In this case, it's David with Oklahoma DOT. And then we'll have questions at the end. However, even though questions are at the end, please go ahead and get them in the chat. It's very common for us to be able to answer them on the fly and even get deeper as we go. So utilize the chat. That's kind of our favorite feature of these webinars. So cracking tests at NCAT, this has gone back, many years, but in my opinion, it seems to have really taken off around 2015. Randy may have he may rewind it even further than that. But in 2015 is whenever we were asking the question. We've got all these cracking tests, dozens of them. How do they relate to field performance? And so these are actually some pictures I took doing my master's thesis, which there's a picture of that. I actually started at NCAT looking at cracking tests and how they relate to predicting top-down cracking in asphalt pavement. So I'm very familiar with these tests, and I ran quite a few of them myself. But it's a really important question because if they don't relate to field performance, then it's kind of useless. And so you've got all these cracking tests. And so in 2015 was really whenever we started a flagship experiment that we call the cracking group, which Randy will talk some more about in a minute. Um, Before we get started, though, lessons learned from my perspective. The test is really only as good as the specimens that are being used, and so we really learn the value of specimen preparation. That's something I preached in my days back at the NCAT lab. Was um, if location, location, and location are the three most important things in real estate, specimen preparation, and specimen preparation seem to be the most important aspects of making good samples for and getting good data from cracking tests. Um, However, you can make great samples and still not necessarily get good lineup with performance. So I'm showing you two pictures here. Again, Randy will dive probably more into these, but this is the same exact mixes with two different tests, and the one on the top, above that green line was little to no cracking, and below the red line was sections that failed. And so the critically aged ideal CT, it actually the lab test lined up with the field tests. Whereas you go to the energy ratio test, which is another test that we ran back in 2015, where the numbers were kind of all over the place, and the lab data did not line up with field performance. So that's why this is such a critical topic. Is you can run any of these tests or all of these tests, but the test is only as good as it has a relationship to field performance. So with that, I hope I kind of set Randy up.
All right. Well, good day, everybody. Nathan kind of set this up. I'll jump right into the outline of the presentation that I'm going to give over the next 20 minutes or so. I'm going to start out with just thinking about what are the objectives of the cracking test? What are we trying to use them for? Talk about different modes of cracking, desired characteristics of tests. I'll mention a little bit about aging effects and how that's important for certain layers. Then I'll get into the really the findings from the NCAT cracking group experiment that was completed. Excuse me, completed about 3 years ago. But I'll also mention a few other validation case studies that have been completed and some that are ongoing as well. And I'll provide a list of just a few references that I think are really important on this topic of the correlation of cracking tests results to the field performance. So first, thinking about how will asphalt mixture cracking tests be used. Probably 15 years ago, when we were talking about cracking tests, we were thinking more about using the test for research purposes. Certainly that has been for a long time what we've used tests like bending mean fatigue, many of the older tests that have been around for a long time. But we realized that we need to get these tests or some tests to evaluate cracking resistance, rutting resistance, moisture damage resistance, other things like that, into the hands of mixed designers and eventually into the hands of the quality assurance personnel, the DOT acceptance test and the quality control test. So that's the direction that we're moving, is trying to develop tests and find tests that are useful not just in research, but for these other purposes as well. So we think about the kind of for those needs, what are the characteristics that we want? If we want this test to be used for quality assurance, then it needs to be simple. And what that means is we may have to have a test that's just a simple monotonic test or a displacement test versus a cyclic test. We certainly want the equipment to run the test and to prepare the specimens and to condition the specimens, all to be relatively low cost, because there's lots of labs out there in the quality assurance world. We also want the results to be fast. We want to get the results quickly, not just in terms of technician time, but the clock time. How long does it take to complete the test, including the conditioning time if that's necessary? One of the other things that I think we've realized is really important over the last 10 years is the result has to have a reasonably low variability. And there's a number of ways that we measure variability. In most test methods, we have within and between lab standard deviations or within and between lab coefficients of variation. So those can be very helpful. The next item is that the test result needs to be sensitive to key mix factors. In the case of asphalt content and cracking, we know that the test needs to be sensitive to asphalt content, to the binder grade, to gradation. For example, it needs to show that SMA has better cracking resistance than dense graded mixes. The result must be strongly correlated to field performance. That's really the purpose of this webinar, is to kind of hit on that key issue. Some people believe that the result needs to be based on fundamental engineering properties. That is true if we want to use the test to do some modeling of pavement response. And some people would like the test to be conducted on field cores. That's actually not a common thing, but it is something that a lot of people have said it would be great if we could do that. So which of these items are the top priorities? Which are the most important? And which are non-negotiable? To me, the one that is most important and non-negotiable is that the test has to correlate well to field performance. If we don't have that assurance, then all the other things, simple, fast, variability, really doesn't matter. So we started an experiment a few years ago that I'll get into in just a second, but we wanted to kind of think about the different types of cracking that we know exist for asphalt pavements. We have bottom-up fatigue cracking, we have top-down cracking, we have low temperature cracking, maybe not in all parts of the US or all parts of the world deal with low temperature cracking, but that is a primary mode of distress in many parts of the US and around the world. And then reflection cracking, where we're talking about an overlay on an asphalt or overlay on a concrete pavement. Reflection cracking continues to be something that we are challenged with. And if we think about all these different modes of cracking, there's different strains. We're talking about different layers. So we have to consider kind of the mode of cracking, the aging that's taking place in those mixes, and the strain levels. So a little bit more on aging effects. One of the things that there's certainly some research on, but maybe it's not well known, is asphalt pavements age, and they age from the top down. In fact, the asphalt surface layers, the top inch or so, ages significantly and rapidly, but the lower layers really don't age very much. And that's important when we start thinking about aging, laboratory aging of mixes to simulate the field. Okay. Then we have to ask the question of how much field aging are we trying to simulate? How many years of field aging is important? Is it 1 year, 2 years, 10 years? And that question kind of comes into the decision about the mix aging protocols. So currently there is an AASHTO standard. It's R121 on mix aging, long-term aging. And there's 5 choices that have all been used and maybe are currently used by different organizations, different states, and different researchers around the country. And there's ongoing work to help us still answer the question of what is the best aging or the most appropriate aging. And there may be more than one choice, but we do have these choices of different aging conditions that we can use. The aging procedure that NCAT has worked on mostly, and I'll talk about in this webinar, is loose mix aging at 135 for 6 to 8 hours. The duration, whether it's 6 hours or 8 hours, depends upon whether it's a southern climate or a northern climate. So getting into this thing that we called the cracking group experiment was actually a partnership between NCAT and Minroad. NCAT, we were looking at top-down cracking, and there's 7 different cracking tests that we included in this experiment, and I'll go through each one of these. Not necessarily the test details, but I'll go through kind of the correlation to the field performance. And we did these tests on both lab-prepared mix and plant-produced mix, and on samples that were short-term aged or plant-produced and those that were reheated. I'm only going to talk about number 4 there, the plant mix samples that were reheated after critically aging. And I apologize for the red laser. That's an artifact of an earlier presentation where it looks like it recorded that laser movement. So hopefully we won't see that again. On the test track, we built 7 test sections, and the experimental layer was only the surface layer, the top 1.5 inches. And we wanted top-down cracking, and we wanted to avoid having bottom-up cracking. So we used a structure with a highly modified asphalt mixture in the intermediate and base layers to be very strain tolerant, so that we would not get bottom-up fatigue cracking. And then we created the 7 mixes in this experiment with a range of mix expected performance in terms of top-down cracking. And we achieved that by just putting in some things in the mixes like polymers or shingles to create different cracking susceptibilities. All right, so now I'm going to get into those 7 tests. I'm going to start out with the energy ratio test, and if you go back 10 years ago in the literature, this was sort of the one that people thought this is going to be the one. This is going to be the cracking test that we need to use. There had been very little research on this outside of the researchers that developed this. So we included it. It's an indirect tensile type test, but with strain gauge extensometers that are glued to the specimen face. What I'm showing on the right is this chart that Nathan illustrated a little while ago as well. The 7 mixes are ranked here from top to bottom by best performance at the top, worst performance at the bottom. And the top 3 mixes in this had little to no cracking. The 2 in the middle had moderate, low severity cracking, and the bottom 2 mixes in these charts failed by top-down cracking, and those were all verified by cores. So energy ratio, a better or higher number was considered to be better by this research, by the previous research. But what we can see from this chart is it did not rank these mixes correctly. Some mixes with low energy ratio failed, did really well, and some mixes with reasonably high energy ratios failed. So it did not show us the correct ranking. Another way to look at the data is just with an XY plot, and on the X-axis is the energy ratio, and the Y-axis is the percentage of lane area cracking. And we would expect, if the test is a good correlation to field performance, that this regression equation shown by the dotted line would fit well, and it'd be a nice kind of linear relationship or a relationship that fit well to the data. R squared is our coefficient of determination, and when that's 1, it means it's a perfect correlation. When it's close to 0, it means it's not so good. In fact, this one's showing it's very, very poor, close to 0. So I'm going to kind of show those 2 charts for all these other tests. One of the other tests that was popular 10 years ago and still is used in research mode is the Texas overlay test. And here you can see very clearly that the test ranked the mixes correctly. Those with the best cracking resistance had little to no cracking in the overlay test. And I should point out that the overlay test beta parameter, some people call this the crack progression rate, CPR. A lower number is better. And the mixes at the bottom of this chart are the mixes that had the highest beta, which means they were least resistant to cracking, and that's exactly what happened with those test sections in the field. These letters A, B, C, D, E are the statistical analyses tests with the same letter indicate that they are not statistically different. But we can clearly see that the mixes with an A were grouped together, mixes with C were kind of grouped together, and D and E were the best, you know. So clearly we see statistical differences in the test result. That means really the test can discern good, moderate, and poor performance. That kind of statistical grouping is important. If we look at the XY chart, you see that R squared here is about 0.79. That's a very strong correlation for a field test under control conditions. So we're really happy with this test as a good indicator of top-down cracking. We also did a modification of the overlay test based on some previous research that we had done at NCAT using a smaller displacement and a faster cycling time. And we see also it did rank the mixes correctly, got good statistical groupings, and we look at the correlation between the lab and the field, and we see this very strong correlation, R squared of 0.97 here, a nice linear relationship. So this is a really good test for the correlation to lab and field. Another test that is used by Louisiana is referred to as the semicircular bend test. And this test, you can see it didn't necessarily do poorly in terms of ranking the mixes, but there are some cases where mixes with moderate to low severity cracking had better test results than mixes that perform really well. If we look at sorry, I'm trying to get my slide to advance. If we look at the correlation, the XY correlation, R squared is only about 0.2, and that's not a very strong correlation. I'm trying to get the slides to advance, and it's kind of going slow on me. Another test that is used and has been very popular over the last couple of years is the Illinois Flexibility Index test, or IFIT. It is used in the state of Illinois. And you see it rank the mixes very well in terms of the ranking versus the field performance that we observed. And the correlation, the R squared for this test is R squared of 0.89 or 0.89. So that's really a really strong correlation. I'm pausing because my computer seems just being slow in advancing the slides. The ideal CT, it's most popular test being used around the country for BMD. It also did a very nice job of correlating with the field performance in this experiment. Good statistical groupings, and the XY correlation very strong, R squared of 0.96. So a really strong correlation between lab and field results. The last test that we ran was the AMP cyclic fatigue test. It also ranked the mixes correctly, as shown on this chart. And the R squared on this was really good, about 0.90. So in summary, we have quite a few tests that actually correlated reasonably well between lab and field. So, between the Texas overlay test about 0.79, we have CR squares up here 0.96, but anything, near or above 0.8 is considered a really strong relationship. Now, some of these tests aren't simple. Some of these tests are not fast. So I think, considering all those characteristics that I mentioned before, we certainly see why the ideal CT test is popular. Has a reasonably good coefficient of variation, has a good statistical grouping, has a strong correlation to field performance. Now that's just one experiment, one set of test sections at one location. We had partnered with Minroad to do a similar experiment in Minnesota, and in Minnesota, the experiment was intended to evaluate thermal cracking or low temperature cracking. And I don't want to go through all of the details I went through for the NCAT experiment, but again, we looked at a variety of tests. We looked at the correlation between the lab and field performance, and that experiment is documented in a separate report. And we see, there are some tests that did have a good relationship between the lab test and the thermal cracking that we observed in Minnesota after 5.5 years. There are other studies that are worth or important to mention. I mentioned the Illinois Flexibility Index tests. They had initially done some correlations with an experiment on the FHWA accelerated loading facility. And then they followed up with some other correlations, which I'm showing a little chart there off to the right, that's really combining data from a research project and their pilot projects in Illinois that shows a good relationship between flexibility index and the rate of cracking that they observe on projects in Illinois. There are other projects that have looked at reflection cracking. There's an NRRA study. University of New Hampshire did the study, and that report's available. And then I've got several other experiments in kind of blue text that are ongoing. TTI has an ongoing project through Capri looking at projects in 5 states scattered across the U.S. NCAT and Minroad have another experiment called the Additive Group. That work is ongoing. Missouri, University of Missouri and the Missouri DOT are doing a reflection cracking experiment. That's ongoing. And then a number of states are doing BMD validation test roads or test sections on open highways. Alabama, Wisconsin, North Dakota, to name a few. And there are more states that are building BMD validation projects this year. So I wanted to list here again some of the references. We'll provide these slides, so people can get to them and click on the hyperlinks that are shown there in orange to actually get access to each of these reports and get further details. So I know I talked a lot of really fast, so I appreciate your attention, and I will stop sharing.
Well, thanks to NCAT for inviting me to participate on this webinar. We've been doing a lot of work in Oklahoma, and it's always good to show it and to have some insights and questions around from other people. So it's always good to have that. Also, in regards of Nathan's comment, yeah, I mean, we all learn to have our lab shoes and and normal shoes. We had an incident with the binder 5-gallon binder bucket that I dropped on my nice shoes. Well, I didn't get burned, so they work. So on shoes are good for liquid binder at 300 degrees. So okay, let's move on to what we were doing in Oklahoma in terms of correlation to field performance of cracking tests. So we've been working on this BMD implementation for a while. We started pretty much in 2018, looking at, what's BMD about? Do we need it? Is this something we want to pursue? And we decided, to move forward with it and start looking at different tests, how we're going to specify this, and pretty much moving, along with the industry on this topic in 2018. Then in 2022, we moved on to, okay, let's do well, in 2018 we did 4 projects, and I'll touch a little bit on that in a while. But then phase 2 was more of a proof of concept. Okay, let's see how the local industry reacts to BMD, and how are they, do they have any issue or challenges with production and, putting together the mixes, stuff like that. We built 11 projects back in 2022. Also, we started looking at the 4-hour aging during design, their short-term aging, and we observed very interesting information on that. And then phase 3 was more of like, okay, let's validate now this short-term aging protocol. We built another few projects. I think it was 3 projects in 2023, and we started working on benchmarking. Sometimes I think the steps for implementation recommended say benchmarking first. So we did benchmarking like 2 years later, 3 years later. So, I mean, it's just the way it worked. But then we picked or selected our criteria of 100 of surface and 60 for intermediate or base courses based on that benchmarking study. Then 2024 was
Hey,
like
David?
yeah.
We're not seeing your screen, or at least I'm not.
Okay, is there
I'm
anybody
seeing it.
else?
I'm
Okay.
seeing it, Randy.
Okay, maybe I've got something in my way. Sorry about that.
Yeah. Just let me know if you guys have any issue with seeing my screen. So, and then 2024 and 2023 and 2024 was when in 2024 and 2025 was when we started, kind of like a broader implementation effort with 8 pilot projects and actually doing testing every single lot. So I'm going to be touching those projects as well. So it was pretty much our BMD implementation journey. I'll say started in 2018. We're still ongoing. So in terms of the cracking test that we look into, at first in 2018, we look into IDLCT and IFIT, and trying to see which one are we going to move forward with. In that case, we did 8 projects, a few mixes, control, and BMDs. So on both tests, 9 out of those mixes passed criteria, but 6 of them were, passed on both tests. We showed a moderate correlation of 0.44. And also we analyze variability, in those tests. So IDLCT showed an overall variability of 20%, and IFIT lower 15%. We typically try to keep that variability around the 20% mark. And then when we go by, nominal maximum on the 12.5 millimeter mixes, pretty much they show very similar results with 17 and 16% COVs. And then we also check sensitivity to mixed components, specifically asphalt content. So we run 3 different asphalt contents on each test on lab fabricated specimens, and we observed that IDLCT had better correlation with R-square of 0.95. So that told us, okay, IDLCT is telling us a bit more in terms of asphalt content. We did additional analysis like random forest and some other stuff, and IDLCT showed to be a bit better on all of them. So with all that, and also, thinking about actual implementation, how are we going to distribute all the equipment, acquire all this equipment, distribute the equipment, and provide training and everything to, field residencies, contractors, and consultants. So we decided to move forward with IDLCT because it was a bit cheaper to implement, and it was way easier in terms of training. And we realized that on 2024, when we started doing actual training on a bigger scale, that how how different was that instead of picking IFIT. I mean, imagining if we would pick IFIT versus the challenge that we observed with training for IDLCT. So I think we made a right choice in terms of picking IDLCT. So the performance test we use in our BMD approach, it's Hamburg for routing. We've been running Hamburg for about 20 years already. So we're very familiar with Hamburg. We consider not to have really a routing issue in the state. So we will continue with Hamburg during design. We don't run it during production, but we don't really see, again, a routing issue. So I don't think we should do much Hamburg testing in the field. And in terms of cracking, I mean, we do a DLCT. Is the one we're using so far. On the 2023 pilot projects, we decided to use 100 for surface and 60 for intermediate mixes on IDLCT, and now we're deploying our general practice space provision that we're going to be running IDLCT for design on actual BMD projects or full BMD projects across the state. So we decreased the requirement a little bit by 90 on surface mixes and 40 for intermediate mixes for that general practice special provision. So in terms of correlation to field performance, so we have two approaches, basically, a short-term approach and a long-term approach. And I'm going to discuss each one of those separately. So for our short-term approach, we rely on accelerated testing facilities like NCAD, and also on research projects. We partner with local universities, OU, OSU, and some others. And we basically, so we have those two approaches. We've been working with NCAD since 3 cycles ago on BMD. So cycle 7, we did BMD and RAP, and we also participated in the cracking group experiment with the section, I think it was N8. That was a control plus 5% RAS mix that ranked last. So we are the perfect example of why we're not using that much RAS.
I designed that mix, David.
Yeah, so we participate in a cracking group experiment, and we always been working closely with NCAD in terms of sharing information, having those supporting or having those test sections. So we actually get a lot from NCAD in terms of information for our specifications and what we want to implement. So cycle 8, we did BMD and high RAP and rubber. And then cycle 9, which is the current cycle, we're working on BMD plus RAP and software binder field validation. I will touch a little bit on that work we're doing. In terms of research, I mean, we're working with local universities, so we do benchmarking studies. We study war mix asphalt benefits for IDLCT or for BMD approach. We're tracking performance on some of the projects, and mostly on the 2018 projects we were the first we built. We went back and we did an analysis and comparing control with super pave control with BMD mixes. So far they're all performing equally, so I think those are really good projects, successful projects with showing equal performance on both. We also did some life cycle analysis, also as well as validation of the short-term aging design protocol of 4 hours that we use. In terms of the test track, current test track study, so we have section N10, and the idea there was to simulate the conditions of State Highway 60, which was one of the projects of 2023 we did in the state. So it's very challenging underlying conditions. You can see the block cracking, a perfect example of block cracking that we had in State Highway 60. And then what we did in the test track is to saw cut the section to simulate that same block cracking. and then basically recreate a worst case scenario and use a mix that was at the edge of our BMD specification. Basically 25% wrap, softer binder. So that was pretty much the most challenging mix we allow in terms of our BMD special provision. So the idea is to put 10 million easels over 3 years on that section. I think so far it's been like around 4 million easels or 5, if I'm not mistaken. I think that mix started showing some cracking around the 3 million easel mark. So for us, that's actually a very successful mix, because that Stay Highway 60 project is actually a 3 million easel design life project. So it's showing us that we can go to that approach of requiring 100 on CT index, and we can use wrap up to 25% with softer binded with acceptance performance. So it's also a bit on the grid. We saw cut in that section, so we did sections of 8x4 feet and 4x4, to recreate that block cracking. So that's pretty much our short-term approach. Short term, we're talking about 3 years tops, which is basically the cycle of test track, and it's typically the duration of our research project with universities. In terms of long term, okay, now let's see, build pilot projects and track performance. The way we did that in 2018 was that we put the control mix in one direction and the BMD mix in the other direction. That represents a problem with our approach of trying to use our payment management system to keep track of performance, because payment management system sometimes only covers one direction of traffic. So in 2023, we decided to design those pilot projects thinking about, focusing on long-term performance monitoring. So we put the control and the BMD mix in the same direction, and then we focus on, using ODOT payment management system to keep track of that performance over time. And 2022 projects, we did the same, and we put all the projects in the same. And the idea of having those pilot projects is that we want to, have real world scenario projects that we're keeping track of. I mean, test track, it's good, so control conditions, but here in the state, we struggle with some extreme, weather conditions that we may not see all the time in the test track. This week, this Monday was 22 degrees, and we're expecting 95 tomorrow. So we have those crazy temperature swings, and this always represents a challenge, for payments. So we want to have real world local projects to keep track and see how are they performing. In terms of designing those projects, again, I think it's an important, part, and it's something we were discussing at the TRB, the committee meeting, where we need to start, as a state agency approaching and partnering with our asset management departments and see, okay, or kind of like making them understand the big role they're going to be taking in terms of keeping track of performance of those pilot projects in the future. They're familiar with condition tracking. They know what they're doing. They've been doing it for a while. So it's important to, partner with them to understand the PMS or payment management system functions and limitations. Again, like I mentioned, sometimes only certain roads are covered by the PMS. Maybe the accuracy and resolution is not what we need, or it might be able to isolate specific sections where you can use a bit more resolution. That's what we're doing in Oklahoma. And also, design those pilot projects thinking about those functions and limitations, place the control and research mixes strategically, using BMD and control in the same direction, locating those transitions, also define sampling quantity and frequency. The idea is to have multiple lots sampling and locating those lots on our, you know, test sections to keep track of performance over time. In terms of an example is what we did for 2024 projects. So during design, we evaluated our mixes with routing, IDLCT cracking. That was for mix acceptance and selection, and also to have, you know, that baseline lab or design data. And then during production, we actually tested multiple lots, basically all of the BMD lots and all of the control lots on the same direction. We not only sampled those, but we also tested those lots in different aging conditions. Hot compacted, you know, compacting right after production without reheating, and then reheated specimens, and then critical age specimens. And that's to have, you know, the full set of results for us to compare. You know, in the future, we can maybe isolate lots that are showing some distresses that others are not showing, and then seeing if it actually matches with what we observe in a hot compacted reheated or critical age production results or IDLCT values. Just an example of how that payment management system looks like in Oklahoma, so we can actually track, you know, the progression of those distresses over time. We do an annual data collection, and we do it in an interval of 100 of a mile. And we measure IRI, rod depth, raveling, macro texture, transverse cracks, and also cracking percentage, which is alligator cracking plus miscellaneous cracking. And those are pretty much the metrics that we're observing or keeping track of in our pilot projects. This is how our report looks like. And it's basically, you know, we have pictures also from all those sections. We can see in the pictures also the stress progression, and also on the 2024 part, for example, where it was right after construction. So we keep track of those metrics over time, and then we'll keep track over you know, a number of years until we actually see some differences. And this is going to take, you know, it's going to take a while, but we need to set us or to work on having these systems in place so we can, you know, keep track of these. I think that's very important. This is a summary of all the projects we're keeping track. Right now it's 11 projects across the state, where we are again checking, you know, IRI, rod, raveling, microtexture, transfer cracking, and cracking percentage over time. So it's a very thorough, you know, progression tracking. So, okay, what are we doing next in Oklahoma? So on 2026 or this year, we're actually deploying our special provision. It's pending approval, but I think it will be approved pretty soon. That will allow us to start, you know, bidding BMD mixes or BMD projects in 2026 as a general practice, like I mentioned before. We're going to keep working towards performance specifications. We're aiming, you know, for that approach D, at some point having, you know, performance only specifications in the state. That's going to take a while, but that's our goal. We're working on, you know, continuing the implementation of cracking tests for QC/QA. You know, the issue right now with the 2024 project testing and data analysis we did was that variability was kind of high or all over the place in some cases. So we want to limit or mitigate that variability to at least 20% COV within lab and between lab as well on those and within lot and between mixes, and, you know, kind of like limit those variability. In terms of designing the mixes or design and approval of mixes, our COV is around 16%. That's why we're moving forward with BMD for design. We also need to determine criteria and testing frequency in the field. That's something we are actually right now doing for information only. We're start testing every 4,000 tons on a DLCT, information only, no pay factors so far. And then we're going to be working on a few more pilot projects soon where we're going to start looking for other options to balance mixes, like using rejuvenators, rubber, maybe some graphene, mix additives and mix, modifiers. And we also want to start looking into BMD impacts on friction. And that's something we're going to be working on maybe the following year. So that's pretty much everything I have. So I don't really have like field performance or correlation information, but we're getting ready for, to having those data as we move forward with our, performance tracking.
So just to kind of close this out, first of all, thank you, Randy. Thank you, David. That was excellent. Excellent. Very, 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 very helpful. To summarize what they said in terms of recommendations, Randy, I liked your list of sort of, with a wish list for what a good cracking test is. And I think I agree. The most effective ones and the ones that are truly implementable are simple, low cost, quick, repeatable, sensitive to mix changes. But first and foremost, they have to be related to field performance. Otherwise, you're just guessing. But it is important to know what distress mode is of concern. If you're doing bottom-up fatigue cracking, you may not be critically aging for as long, or aging for as long as top-down cracking test. Or we didn't talk about rutting, but if you're looking at rutting, there's no need to to age long-term. So it's important to make sure that the test lines up with what it is the primary mode of stress is that that you're concerned with. Our friends up in the north in Minnesota, they run the DCT test because they have low temperature cracking, which I don't even know what that is. I live in Alabama. So with all that being said, though, I think tests with good correlation and that have low variability, those are the ones that can truly be used in a mixed design system. They need to be repeatable and they need to line up. And if it's a bonus that they're cheap and quick, that's a bonus, but those things are important, but they're slightly less important than it's got to be repeatable and it's got to be real. It has to actually line up with what you're seeing in the field. But consider the impacts of aging. I think there's some questions going in the chat, which Randy, I'm actually going to ask you to elaborate a little bit more on in it. But what are you trying to simulate? And that would help you as you try to select one of those. I think there's 5 long-term aging procedures that Randy discussed. How long are you willing to wait? Is this something you're trying to do in quality control, design, research? Those are all important questions as you select aging conditions. And then, David, I really liked what you were talking about. And Randy, you hinted on this, but David, you really dove deep, and I thought it was excellent. Controlled field validation experiments are the gold standard for determining field correlation. Mining through PMS data, and doing big laboratory studies or benchmarking studies looking backwards, that's useful, it's helpful, but there will always be things that you can't capture the effect of, maybe differences in base stability or differences in age or materials and absorption and all these things that if you are building these things for the purpose of figuring out what test you want to use or what the threshold should be, controlled field validation experiments are the gold standard.
Nathan, I'll jump in there real quick. There's on the Capri website, which is capriasphalt.us. There's a guide for doing field validation work, and it talks about the different ways of that states are trying to establish criteria. But as you've got it summarized here, I really think that the best approach is doing field experiments, field test sections in the state with the materials, with the aggregates, binders, construction techniques that you use. And you're going to see for your materials, your data for whatever cracking test will be different than what we show. So if you're going to set a criteria, it needs to be based not on NCAT's data, it needs to be based on your own data. The real negative with doing those field experiments is you're going to have to wait a while to see the results. And it may be, 5 years before you have results that are meaningful between what works and what doesn't work in terms of mixed cracking resistance.
Yeah. I think part that the test track can play in this is we can help make sure you're not barking up the wrong tree. Do some preliminary stuff like David was talking about, the saw cuts that we did on the track, putting their low volume BMD mix on there. And it seems to be lining up pretty well, but ultimately they're going to place that, in Oklahoma to assess it. And I was, the time, to Randy's point, what I was going to say is the best time to plant a tree was 20 years ago, and the next best time is today. So it's going to take time, but if you do it now, you won't be kicking yourself 5 years later, wishing you had done it. So with that, I guess we got some time for Q&A, and I think the chat's filling up. Let's see, Randy, you answered a couple of these already, but I was wondering if you could go back there was a question about simulating the effects of moisture and.
I've got it for you right here. So the question is, the way it was typed in there says field aging is due to multiple effects. For example, temperature, moisture, freeze thaw. So the question is, would it make sense to mimic that in the lab as well, and a cracking test core respond accordingly to multiple aging effects?
Yeah,
Thanks for
and
that question,
so
Jonathan.
I,
Randy, go ahead.
I gave an answer to that question in the chat, and I'll try to
Mhm.
just give it for the sake of everybody being able to kind of hear me say that. But yeah, there probably are a number of factors. Moisture may play a role, some other things, but the dominant factor for aging is just oxidation, and oxidation is really affected by permeability, air permeability, so interconnected air voids. We have an ongoing study right now sponsored by Florida DOT that's really showing that very clearly. But the point is, we simplify the aging process in the laboratory and just use oxidation of the binder. The binder is the only thing that's really aging. Rocks, they're not aging much, if any. And we're using higher temperature to accelerate that oxidation process. So we're doing that by convenience and simplifying it so that we can get results quickly and get an answer quickly and decide, whether or not the mix has got suitable cracking resistance. So sometimes we do simplify things. We simplify the process, or we simplify the rate at which we do things by doing accelerated conditioning. We have an accelerated weathering system at NCAT. There are not very many of them around the country that does both weather, UV light, temperature, and moisture. And we use that accelerated weathering system in some of our research, but it is very time-consuming process just in itself. I think it takes about a month of aging in that weathering system to simulate a couple of years in the field. And so that's just not useful for day-to-day mix design or QA practices.
Randy or David, jump in. Another question from Kevin Vaughn. Kevin says the NCAT study showed that a CT index of 15 was a good limit for identifying good field cracking. Many DOTs are setting much higher limits in the range of 70 to 100. Is this difference due to differences in aging methods, or are we setting limits too high?
Yeah, it's a great question. And obviously, the mix results that I showed you there was critically aged mixes, not the plant-produced mixes or lab-produced mixes. So the numbers that you're hearing from some of the states, like 75, 100, even 125 in some states, those are not on aged mixes. So got to be very careful about, reading the results. You need to read those details in the reports before you try to set criteria.
Yeah,
David, do you have a comment on that?
Yeah, just tell a little bit on that. Also, talking about control conditions. Those experiments were done under control conditions. and over, a base of HIMA material, which is basically 4 inches of HIMA or something like that. So we don't really see that. I mean, that's not the case for most of the DOTs, in the real world. So yeah, you want to set your criteria based on your local conditions. We did a benchmarking study to pick that 100 threshold, and that was done for the pilot project specifically. And the idea was to have a sufficient difference between our super pave mixes and the BMD mixes that we were going to evaluate on those projects. So ideal CT of 100 falls around the 70 percentile of our mixes on that benchmarking study. So pretty much we're picking the top 30% performing mixes in our, normal practice to compare those with regular or controlled super paves. That's why we picked that 100, and that's why for general practice we went down a little bit to 90 on surface mixes, because that falls on the 60% or 65 percentile. So we're giving a bit more, flexibility in terms of that.
So a question related to field thresholds. Somebody asked, how often should thresholds be revalidated with new field data, especially with continuous improvements to mixes in terms of new additives or higher percentages of RAP and so on?
That's a great question. And I think if we see significant, changes in our mix compositions, see additives that we didn't have that correlation established for early on, then yeah, we need to revalidate that criteria. Those mixes may not perform the same way that conventional mixes do.
Well, I got one more. Actually, I have two more questions. One of them is from Kevin again, and then I have one. Travis, you got a question?
No, I was just going to bounce this one in there from Jonathan. So go ahead.
I lost it. Another question. Some DOTs are experimenting with high mod. Those of you may know that's the high polymer modified binder with low voids and very fine mixes, like Utah. I don't know if those are very fine. I'll have to double check that. But either way, with high mod mixes with low voids, high asphalt content, high polymer content, et cetera. And they're finding these perform really well in Reading and Crack. So how well does the ideal CT test work for these mixes that are really pushing the boundaries of what we're used to?
Yeah. So in the cracking group experiment, one of the mixes that we had there was, it's not the same as the Utah high mod, but it was a highly modified binder. It was the second best performing mix in the lab. So good CT index, good IFIT numbers relative to kind of the other mixes with conventional 7622 and so forth. So yeah, I think those tests too show that those mixes with highly modified binders are good or better.
I've seen numbers in the hundreds. Oh, sorry, David. Go ahead.
Yeah, no, we observed something similar with our benchmarking study. Most of the rich intermediate layers that we use, we're testing higher than the regular super paves, and we're actually developing a mix that we're calling it balanced intermediate layer. It's very similar to rich intermediate layer, but it's a bit higher nominal maximum size. So you can put a bit more traffic in them right after construction, so temporarily. So and yeah, and we have a criteria of ideal CT of 100 on that mix, but it's still a work in progress, but it looks pretty good. We used it on I-35 recently, and it was a really good success.
Travis, Nathan, do y'all have another webinar on high mod?
We don't have another one scheduled right now, but certainly something that we love talking about.
Yeah, we don't have a lot of data with kind of the Utah approach with low voids, but I think that's worth a separate webinar.
Yeah, we agree. I think we're scheduled out through June or July right now, and so we'll add it in.
Yeah.
Yeah.
Hey, there's another one that came in here that I think could be nice to bounce in real quick if we can.
Yep.
Randy, you had the slides that showed very much that the oxidation occurs in the top layer of the asphalt, and it ages less as you get deeper down in there. So one person had a question, Jonathan did, about how does that loose mix critical aging really compare if the majority of our mix is not aging as much as that surface?
Yeah, it's a real gradient. And so we're not simulating that gradient, but if we're just talking about the surface mix, the only way to kind of create that accelerated aging is throughout that mix is through a loose mix aging. So it's again a simplification. Um, Illinois does aging on the compacted specimen, and they're probably see, that if you sawed up and sliced up that laboratory compacted specimen aging, you'd see it's aging from the outside in. And when you do any kind of cracking test, you're really testing the center part of the mix. So anyway, the point is, um, we're just trying to accelerate the oxidation of the binder in the mix. We know that there's a gradient, and we would not recommend long-term aging for any mix other than the surface mix.
Let me, so there's some chat going on about the Utah High Mod spec. So feel free to check that out. I want to ask one more question and then close this out, Randy. And David, I'd like to hear your opinion on this as well. Randy, I was wondering, could you talk a little bit more about balanced mix design tests and as a predictor of are we predicting field performance in these tests? Is that the ultimate goal, is prediction?
No, we're trying just to make a decision whether the mix meets the specification. And so we're setting criteria based on expectations of good performance. There is certainly interest of, trying to use these tests or parameters within the tests in models that can be used to, predict performance. But as I showed, there's different modes of cracking, top down, bottom up. There's reflection cracking and all these different modes of cracking. So the models would have to, simulate each of those stress conditions independently. And really, I think that's kind of the direction we're moving toward. But right now, that's not what we're trying to do. We're not trying to predict performance. We're just trying to evaluate resistance according to a criteria that we're trying to establish.
David, close us out with your thoughts on that question, please.
No, well, I agree with Randy. I mean, we really don't want to, we're not predicting really performance with these tests. The way ODOT says it is that we are weeding out mixes that could underperform, and we're trying to avoid to put those on the roads. And that's pretty much the approach we're taking with IdealCT and with this cracking test right now.
Yep. You're weeding out. I like that. Well, thank you both, Randy, David. I think I say this every webinar this year so far, but this has been one of the best ones. But so it was highly attended, and I thank you, both of you, for your time and your expertise. So with that, Travis, I'm going to kick it to you.
Cool. So if you want to check out and see other research that's going on, or go historically on the things that we've done here at NCAT, please take your opportunity to visit us at our website, which is ncat.us. You can get into the test track information there, and we've kind of shown on the screen here, some of the key findings over the 25 plus years that the track has been in operation, and then you can look at each of the cycles there. Training in your pocket is something that we love to share. It's quick YouTube videos that hit really high level. Great for folks that are just coming on in the industry, or if you want to peek into something. There's also some what we call training in your pocket in 90 seconds that are coming out to those little bite-sized chunks there. You can always jump on and see what training opportunities that we have. We actually have our asphalt mix design course in session right now in another room in our building. And then next month, please join us. As always, this is reoccurring every third Thursday at 10 a.m. Central. Next month, we're going to talk about the use of asphalt inner layers to mitigate reflective cracking. We've got a good lineup there, some great work that's been done at the NCAT test track, and one of our good friends, Phil Blankenship, is going to be joining us as our as someone who's been implementing this kind of stuff. If you ever see a QR code and this logo together, that QR code always takes you to what the next one will be. So I got to hurry and flip that over here in just a moment, and we'll be set to go. So, given that, I appreciate everybody's time. Randy, David, I appreciate you, everything you've done for us today here. This has been really great. One last thing to kick in there, the question about the thresholds and how often they should be reevaluated. That comes from Jay, who's in Hawaii, who must have got up around 3:30 or 4 in order to be to our webinar this morning. So we're glad to have our partners, John and Jay, that often attend these webinars. So given that, everybody have a wonderful day.